All right, so now let's talk about reactions of dienes, and in particular, the electrophilic addition to conjugated dienes. So let's sort of stop and remember that when we were talking about alkenes in chapter 8, particularly 8.4, we know that they react with hydrohalogens in this process called electrophilic addition. What's going to happen? First is proton transfer. So this pair of electrons is going to reach out and grab that proton, which is going to break this bond here. Remember that if this is a hydrohalogen, this is a really acidic proton, so it's a really easy bond to break. What's behaving as the nucleophile and what's behaving as the electrophile? Remember these terms from back in previous semesters. The nucleophile is the pi bond. The electrophile, the one accepting the electrons, is going to be that acidic hydrogen. Okay, so just remember this terminology. And that creates a carbocation intermediate. Let's get rid of that real quick. Remember that the carbocations they differ in stability depending on how highly substituted a carbon is. Okay, so in this particular example, the positive charge goes on this carbon here because it's a tertiary carbon. There are 1, 2, 3 carbons around it. And the more highly substituted the carbon, the more stable the carbocation. All right, so then what's the next step? Well, now I have this Br minus, this bromide ion that is now going to attack that carbocation. Now what's playing the role of the nucleophile and what's the electrophile? Here, the electrophile, the one that really wants the electrons, is my positively charged carbocation, and the nucleophile is my bromide ion. And so I have this addition to this double bond. So notice what I started with was my alkene and HBr, and then I have this addition reaction. Just to be clear, this hydrogen here is now on that carbon there. Okay? When I have a conjugated diene, I'm going to get a very similar type of reaction. However, there's actually 2 products that could be obtained. And notice the difference between these 2. So here, if I'm going to label carbons, 1, 2, 3, 4. Here I have 1, 2, 3, 4. I have the bromide on carbon 3, but my double bond is still between carbons 1 and 2, just like it was on my reactant side. Okay, this is different than 1, 2, 3, 4 over here. Now my bromide's on carbon 1. Importantly, though, my double bond has moved and is now between carbons 2 and 3. Right, there was no double bond between carbons 2 and 3 on the reactant side. Okay, so something's different. Something's going on here that isn't just either the bromide adds to this double bond or it adds to this double bond, and that's explaining these 2 products. There's something deeper at work here. Okay, one thing that's important to remember, and this is sort of what I was saying before, let's look at these carbocations on a scale here in terms of increasing stability. We said that methyl and primary carbocations were so weak they basically don't form. And then in terms of increasing energy, it's second and tertiary, but even more stable than that is an allylic carbocation, or a carbocation located 1 removed from a double bond. Let's actually do some terminology real quick. Oops. These positions on either side of the double bond, these were called vinyl carbons. The allylic position is 1 removed. So this particular compound has 4 allylic positions. So a carbocation located at any one of those 4 positions, at any allylic position, is even more stable than a tertiary carbocation. So one of the things that you need to make sure you're doing when you're doing the reaction mechanisms for these reactions is you're always forming that allylic carbocation. So why does that matter? So let's go through this reaction real quick. All right, so just like before, my pi bond in my alkene is going to play the role of the nucleophile. So this is going to reach over and grab this, and that's going to break this bond there. And that's how I'm going to get my carbocation that's formed. Importantly, it's formed on the tertiary position. Okay. But now I have this allylic carbocation. There was another thing that we learned about these last semester, which were pretty special, which is that they can sort of participate in resonance. So this bond here can move over by attacking that positive charge. And by doing so, I have shifted where my double bond is, as well as where that carbocation is. Okay. What does not happen is something like this, where I form this, where the hydrogen attaches to the second carbon and I get a primary carbocation. It's not just that you don't form a primary carbocation, it's that you always form the allylic. Yeah, primary carbocations are absolutely not going to form. But most importantly, you always form that allylic carbocation. So it should always be located in the allylic position to the other double bond that has not undergone addition. Okay, so now we get to this situation where, again, if we're just going to sort of draw it out, we have our double bond playing the role of a nucleophile, attacking that electrophilic acidic hydrogen. And then we have these two different resonance structures here. Well, so this is where these two products arise, right? I could have the bromine come and attack this carbocation here, but I could also, if I'm just going to color code, have this pair of electrons move over and take me to this structure here. And now the bromine can attack that carbocation. So that's the name, sort of why these two products can arise, right? One, you have just your regular old vanilla addition, and then the other one arises because of resonance of that carbocation. Note that this product here would be called the 1,2 addition. Why is that? Well, because 1, 2, the hydrogen that got added is exactly one carbon away from the bromine that got added. And this would be the no resonance product. We also have the 1,4 addition, and that's because the hydrogen that got added is 4 carbons away from the bromine that got added. And this is the one that occurs because of resonance. Resonance. There it is. Okay, so this is this nature of this 1,2 addition. You can also have the same thing if instead of using HBr, you use Br2. You could also get the 1,2 addition. Again, those two bromines that are added are located 1,2 away from each other, or the 1,4. So same sort of deal that if you same sort of deal as if you had HBr. Okay, what's really interesting about these two products, the 1,2 and the 1,4 addition, is the ratio of the two of them is dependent on temperature. So if you do this at really cold temperatures, 0 degrees Celsius, so freezing temperatures, you'll find that you have more of your 1,2 addition product and less of the 1,4 addition product. If you do it at high temperatures, it's the reverse, right? So at 40 degrees Celsius, that's like 100 degrees Fahrenheit or something like that, pretty hot. You now get less of the 1,2 than of the 1,4. Okay, so the rest of this lecture is going to be exploring why that is. If we wanted to diagram that out with one of these potential energy diagrams, this is sort of what it would look like. And this has two key parts. So notice that for both of these pathways, the proton transfer step is the same, right? It's what happens after that that's different. So if we zoom in here, there's two main features of this curve that are different. One is the height of this barrier. Let me actually use the same colors. One is the height of this barrier here. Remember, we call that the delta G double dagger, or the activation energy. Delta G double dagger for the blue is smaller than the delta G. Oops. hashtag, then the delta G double dagger for the red, right? So this is, and again, 1,4 was with resonance, and the 1,2 was without resonance. What did the activation energy correspond to in a reaction? Activation energy corresponds to the speed of a reaction, otherwise more fancily termed the kinetics of a reaction. Okay. The other difference is the difference between the starting product, the energy of the reactant and the product, which we call the delta G of the reaction. And in this case, delta G of the 1,2 is going to be smaller, both are negative, which is important, but smaller than the delta G of the 1,4 addict. Okay, and this is what does delta G correspond to? Thermodynamics. Really, this means that the 1,4 addict is more stable than the 1,2 addict. So these are actually reverse sort of things. Even though the sort of, in both cases, we're saying that the delta G of the without resonance is smaller, it means different things when we're talking about regular old delta G and delta G double dagger. It means that this reaction, the 1,2 is quicker, but that the 1,4 is more stable. Okay, that's what this potential energy diagram just showed us. So the 1,2 being quicker, we would say that it is kinetically favored, meaning it forms more quickly because it's got that lower delta G double dagger, lower activation energy. The thermodynamically favored is the 1,4, meaning that it's more stable, right? So the product that you get is more stable. The reaction is slower, but the product that you get at the end of the day is more stable. It's more thermodynamically favored. I'll put in the lecture, I don't remember off the top of my head, I'll put in the lecture notes where, I know I want to say it's chapter 6, but I'll put in the lecture notes above this video where exactly you can look for an explanation of activation energy versus delta G. So first of all, let's tackle why is the 1,4 addict more stable than the 1,2 addict? That's pretty simple explanation there. And it just has to do with the fact that the more highly substituted alkene is generated with the 1,4 addict than the 1,2. Right? So as we had said before, more highly substituted equals more favored. Here you have these 2 alkyl groups and 2 hydrogens for the 1,4 addict versus 1, 2, 3 hydrogens and only 1 alkyl group for the 1,2 addict. Okay, so the 1,4 is just when you have that double bond that gets kicked over, it's just going to be a more favorable product that's formed. And then when we have the 1,2, it forms faster. So why is that? Presumably it's due to proximity effects, meaning that when this, this first step occurs, this hydrogen joins on, and then you have this carbocation that forms. Well, the bromine's sitting right there, right? It's directly next to that carbocation that's formed. So it can quickly join onto that carbon compared to the 1,4 addict, which has to undergo resonance, and then the bromine has to migrate all the way over there to that carbon, right? So, I mean, this is sort of a simple argument that's like, just look at the length of these arrows. That's the distance that bromine is going to have to travel in solution in order to get to that carbocation. Okay, so this proximity effects explains why the 1,2 addict forms faster, okay? And then let's just go back to this here. Notice that lower temperatures favor the kinetic product. Why would that be? Well, at lower temperatures, things aren't moving around as quickly. So the fact that that bromide has to migrate over 4 carbons away, it's just less favorable to happen. There's less collisions, there's less movement going on in solution. At high temperatures, the thermodynamic product is favored, because then you do have a lot of motion going on. And so then it's that delta G that's going to dominate, the fact that you want to form that more stable product. And this is always going to be the case. We're going to see that lower temperatures will always favor the kinetic product for a reaction, and higher temperatures will always favor the thermodynamic product for a reaction. At 0 degrees, you get what's called the kinetic product, which is the 1,2 addict because of the proximity effects. This is always true for every example, right? So in this particular example, it was 1,3-butadiene. This will always be true for any example, any conjugated diene. 0 degrees will always favor the kinetic product. And furthermore, the kinetic product is always the 1,2 addict because of that proximity effect. It doesn't matter what diene you choose. In the case of 1,3-butadiene, at 40 degrees Celsius, you get the thermodynamic product, and that was the 1,4 addict. At higher temperatures, you will always get the thermodynamic product. This is also always true. However, there may be some examples where the thermodynamic product is not necessarily the 1,4 addict. Remember, the thermodynamic product is going to be the most stable alkene, meaning the more highly substituted alkene. That's not always going to be the case that it's the 1,4 addict. So let's see. So in the case of 1,3-butadiene, that is the case, right? We went through all that example. You can watch the previous lecture video, convince yourself of all that. But now let's look at another example where that isn't the case, okay? So first of all, again, at 0 degrees, you're always going to have, or low temperatures, you're always going to have the kinetic product. And that is always the 1,2 addict because of that proximity effect. Okay, so let me actually get black. So starting out with my alkene here, what happens is, oops. We have addition to our double bond. That double bond acts as a nucleophile, grabs that hydrogen. That electron jumps onto the bromine. Importantly, that forms an allylic carbocation. Remember, the positive charge is always going to go in that allylic position, meaning it's sort of like next to the double bond. That means that the hydrogen gets added over here. This molecule is symmetric, so it didn't matter which double bond I chose. If it's an asymmetric molecule, you'd have 2 1,2 products, okay, depending on which double bond you start with. And so because of proximity effects, the bromine will always go on this carbon here. And so this is my 1,2 addict, all right? Cool. So that's always going to be the case. At degrees, you get the kinetic product. The kinetic product is always the 1,2 addict in these reactions. But now for 40 degrees, we know that we're going to favor the thermodynamic or more stable. Okay, so what we're going to have to do is figure out which one, the 1,2 or the 1,4 addict, is more stable, right? Which one's going to form the more highly substituted double bond? So we already know what the 1,2 looks like, right? But in this reaction, oops, that's kind of messy. In this reaction mechanism, we have the carbocation that's formed, same step, same first step as we did over here. But the difference is now we could have resonance leading to the 1,4 product. So now that puts my positive charge on this particular atom, and my double bond has been moved over here. And so when the bromine gets added, it will be added to that positively charged carbon. I'm going to sort of clean up my geometry here. And so this would be the 1, 2, 3, 4 addict, right? This is the 1,4. Let's call it 1,4. Now the question is which one of these is more stable, the 1,2 or the 1,4? And it's actually the 1,2 that is the more stable product, because look at this double bond here. This has 2 carbons, 2 hydrogens, and this has 3 carbons bound and only 1 hydrogen. So the 1,2 addict is actually the more highly substituted product, the more highly substituted alkene. So in this particular example, it's both the kinetic and the thermodynamic product. So it's not the 1,4 that's going to be formed at higher temperatures. It's also going to be that 1,2. Now, I guess I need to move this. So you're not going to get the 1,4, you're going to get, again, that 1,2. In this case, the 1,2 addict is both the thermodynamic and the kinetic product. So it would be the product of this reaction, whether it takes place at 0 degrees Celsius or 40 degrees Celsius.